Hello. In this video, I'd like to cover section 4.5 of Wessel's notes, which is on two-way analysis of variance. And the application here is to test among means of multiple treatments or samples, sampled populations, as well as testing among means of different categories or blocks within the samples. So let's return back to our example of our porosity measurements in our petroleum engineering class. Again, there was one core of a sandstone broken into 4 separate plugs. And 5 students were asked to measure the porosities of those 4 different plugs. So there's one source of variance may be to the different measurement techniques or skills of the 5 students. And that could be that the variance associated that would be called the variance associated with treatment. Another source of variance could be due to true differences in porosities between the 4 plugs. So across the 4 different plugs that each student measured. So a two-way Anova could be used to determine whether all students are measuring the same mean porosity, as well as whether the porosities differ or are all the same between the 4 plugs. Another example is given in Wessel's notes, in which shale is measured at 4 different locations for the nickel content, and at each location the nickel content is measured in 3 different depths. So a two-way analysis of variance can be used to determine whether the nickel contents varies between location, as well as whether the nickel contents varies with depth. And to do this, we need to separate the variance associated with each source or each difference. So let's consider our nickel content example. And so let's define some quantities. So mu sub ij is the population mean of the ith treatment, which in this case is location, and the jth block, which in this case is depth. Mu is the grand mean of all locations and depths. I should say all 4 locations and 3 depths. And then let's call alpha 1 the differences due to treatments or location, and then beta being the differences due to blocks or depth. Okay, with that we can describe mu ij as equal to the grand mean plus the differences associated with location plus the difference associated with depth. And we can define a null hypothesis, 2 null hypotheses, that alpha 1 equals alpha 2 equals alpha 3 equals alpha 4. Those are all 0. The differences are all 0. And the second null hypothesis is that all the block effects are 0. So to test these hypotheses, we'll follow the same reasoning as we did with one-way Anova, and we have to define another sum of square deviations, and those are associated with the blocks, or in this case, depths. And this, well, let's see. Let's go back to defining the sum of squares associated with the traces, and that was 1 over n times the sum of I equals 1 to k different sample locations of t squared I minus the total squared, the sum of all the measurements squared, divided by the number of all the measurements. Remember that ti is the sum of xij, the sum over all the depths of the ith location. So we could write a similar equation for our block effects as 1 over k, the number of samples, and we're summing from j equals 1 to n of t squared j minus our total sum squared divided by kn, the number of total measurements. And t sub j is the sum of the measurements across all the depths. I'm sorry, across all the locations. There are k sample locations. So the total, so you're summing all the measurements at the jth block or depth. To get this quantity tj. So again, SSTR is proportional to the variance associated with different treatments, or in this case, location. SSB is proportional to the variance associated, attributed to differences in depths or blocks. And the total sum of square variance is proportional to the sum of all the measurements squared minus t bar squared over the number of all the measurements. Finally, we have the residual, or the sum of squares associated with errors, or everything other than location and depth, and that's equal to SST, the total, minus SSTR plus SSB. So that's what's left over. So we have these 4 equations that we'll compute our statistics with. And of course, we need to create our Anova table. And I've already sketched this out here. So we have a column for source, a column for degrees of freedom, again a column for sum of squares, mean sum of squares, and Fs. And here we have 3 sources of variance, one due to treatments or locations, one source due to blocks or depths. We have everything else, and then we have the total. For the degrees of freedom, the treatments or the different locations depend on k different locations. So the number of degrees of freedom is k minus 1, which in this case is 3. For the blocks, this depends on n totals for each depth. And so the degrees of freedom there are n minus 1, which in this case is, it's 2. And then the error, so the total, let's go for the total here, kn minus 1, in this case is 11. And the degrees of freedom associated with what's left is just the difference between the total and, in this case, 5, the sum of the degrees of freedom for the blocks and treatments. And that gives k minus 1 times n minus 1, which is 6. Okay, to fill in the sum of squares column, we have SSTR, we have SSB, SSE, and SST. The mean sum of squares is simply SSTR for the treatments over the number of degrees of freedom. The mean sum of squares for the blocks is SSB over n minus 1. And then the mean sum of square associated with everything else is SSE over k minus 1 times n minus 1. So let's look at, so when we fill in, substitute these numbers and compute these quantities, we get 1260 for the variance or the sum of squares associated with location, 1256 as the sum of squares for different depths. The error gives 406, and the total is 2922. The mean sum of squares is 420, 628, and 67.7. So to test our first null hypothesis that the means among the locations are the same, we have to compare the variance associated with location, MSTR, to the variance associated with our error, our residual. And we get an F value of 6.21. And the critical F value let's use a significance level of 5%, and that's F evaluated at a probability of 0.95 with 3 and 6 degrees of freedom, and that is 4.76. So based on a comparison between our measured value of F and our critical value of F, so we have F, so this is for the locations. F is greater than our critical value, so we would have to reject H0, that the differences associated with location are 0. So the second F quantity is the ratio of the variance associated with depth divided by the variance associated with the residual or the error, and that gives a value of 9.29. And so the critical value for F is F again at a probability of 0.95 for 5% significance. Again, we're looking at the right tail of this F distribution, and the degrees of freedom are 2 in the numerator and 6 in the denominator. And the critical value there is 5.14. So again, our critical value exceeds our measured value of F is greater than our critical value. So for depths, the variance associated with depth, again, F is greater than F critical, and so we have to reject H0, that the differences associated with depth are equal to 0. So this was an illustration of a hypothesis test which caused us to reject both null hypotheses. And so we would infer that the nickel content of our shale varies with location and depth. That is, the mean nickel content varies. Okay, so that is an illustration of two-way analysis of variance, and I'm going to conclude with that.